My name is Aleksandr. I work as a senior software engineer at GridGain, and today I would like to discuss the topic of storage engines and the corresponding changes in the fifth alpha release of Apache Ignite 3. So today I will be talking about the new feature that is coming in Ignite 3 and which allows you to specify multiple storage engines. We will also have a quick dive into different storage engine implementations so that you will be able to understand the advantages and disadvantages of particular storage engines and when and how to use them. Let's start with a quick recap of what a storage engine actually is. Formally, a storage engine is a software module that a database management system uses to create, read, and update data from a database. Basically, storage engines are responsible for organizing your data in a way that will allow you to efficiently read or write data to the underlying storage system. In order to achieve that, storage engines use different data structures which have their own advantages and disadvantages and which dictate how and when to use them. Many existing database management systems support multiple storage engines. For example, apart from the default InnoDB storage engine in MySQL, you can also store all your data in memory by using the memory storage engine. Let's have a look at the storage engine used by Apache Ignite 2. As many of you know, Apache Ignite organizes your data into pages of fixed size, which can have different type depending on the type of data that they hold. Here on the picture, we can see a bunch of index pages which store the SQL indexes and some data pages which store the cache entries. As for the data structures that I mentioned earlier, Apache Ignite uses a couple of them. First of all, it's a B+tree, which is used to organize the pages so that they can be efficiently searched for a particular value. And some additional data structures such as free lists or use lists are used to store partially free or completely free pages so that they can be reused during data insertion later. This is also a very flexible storage engine because you can configure it to store all your data in memory or to use the native persistence feature by with the help of the checkpoint process and the page replacement mechanism. However, regardless of the flavor of the engine, whether it stores all data in memory or it stores the data on the disk, the underlying data structures remain unchanged. Now let's have a quick look at the B+tree implementation that is used by Apache Ignite. I understand that many of you may be familiar with this implementation, but I think it's quite important to have a quick recap so that we can later compare it with the alternative implementation. So in Apache Ignite, B+trees are organized into special types of pages, which are called inner pages and leaf pages. Inner pages consist of so-called items, which store links to other pages and the corresponding key values. Here's an example of how this tree might look like. Please note that this is a very simplified example because I'm using integer keys and I'm also omitting some nodes in order to keep the picture smaller. So in this picture, on the level 1 of the tree, we can see an inner node with an item with a key value of 6, which points to two leaf nodes, one that holds the keys with the values of 1 and 3, which are all smaller than the inner node key value, and the other one points to the leaf node with a value of 9, which is larger than the value of the inner node. So unlike inner pages, leaf pages can only contain key values and links to the particular pages over which this B+tree was built over. Additionally, every level in the tree is organized into a linked list, which allows you to optimize some operations such as range scans, for example. So when searching for a particular value, you should simply perform the search tree traversal, which is quite obvious. However, when inserting or removing data from the tree, you may encounter some problems. For example, when inserting a particular value, the target node might already be full, and you will have to create a new page to hold it. And you might also need to split the parent nodes as well, because they might also get full. When removing the data, you might need to split the parent nodes as well, because you need to maintain the invariant that every inner node in a tree must have a minimum amount of children nodes. So basically what that means is that a single logical write to the tree may result in modification of multiple related pages, and this phenomenon is called write amplification. Now let's look at Apache Ignite 3 and the new feature that it introduces. So now Apache Ignite is no longer tied to a single storage engine implementation, and apart from the B+3 storage engine that was ported from Ignite 2, we also introduced a new storage engine which is based on RocksDB. RocksDB is a popular persistent k-value store which is built on top of a data structure called log structured merge tree, or LSM. Let's have a quick look of what it looks like. So in RocksDB, every write first goes into a sorted in-memory data structure called a memtable. After the memtable size exceeds a certain threshold, it gets copied into an immutable memtable, and later gets flushed to the disk by a background process. When an immutable memtable gets saved onto the disk, it is placed into an immutable file called sorted string table, or SST. These SST files are organized into levels, and when the number of SST files in a particular level exceeds a certain amount, they get merged into a new SST file and then later pushed to the deeper level, similar to the merge sort algorithm. This operation is very efficient in terms of input-output operations, because it only operates with continuous regions on the disk. So writes to this data structure are quite simple. You only need to add the value to the memtable, and it will be later copied to the disk. However, when searching for a value, you first need to perform binary search over the memtable and over all immutable memtables, as well as all the SST files that currently reside on the disk. This means that a single logical read may require you to scan over multiple files on the disk, which is called read amplification. So having looked at both implementations, let's discuss the pros and cons and understand when to use one storage engine or the other. So as I have said, B+3s are susceptible to write amplification, because a single write may require you to update related pages, which can require some random input-output operations. On the other side, LSMs suffer from read amplifications because you need to scan over multiple SST files. This might lead to a conclusion that B+3s are better suited for read-heavy workloads, while LSMs are better suited for write-heavy workloads. However, in real-life implementations, these data structures are designed in a way to overcome these disadvantages. For example, the B+3 implementation in Apache Ignite uses a checkpoint buffer in order to accumulate as many modified pages as possible, so that later we can sort them in a way that we can arrange them into continuous data regions, and then later write to the disk more efficiently. On the RocksDB side, they allow you to specify very aggressive compaction strategies, which basically dictate how many SST files are present on the disk at every given moment. They also use a technique based on Bloom filters, which allows you to quickly understand if a particular key is present in an SST file without having to perform the binary search. So what this means is that even though B+ trees are susceptible to write amplification and LSM implementations may suffer from read amplification, in the real-life applications, you should always perform deep analysis of your application workload and try it out with multiple configurations of the storage engines. Finally, let's have a look at the new API that is introduced in Apache Ignite 3. You can specify a storage engine when creating a table through the SQL API by using the engine keyword. Currently, there are two storage engines. One is LSM-based called RocksDB, and the other one is the B+ tree based storage engine from Ignite 2, which is called page memory. Storage engine configuration is expressed through the data region concept, which can be adjusted by the Ignite CLI tool. There's also a notion of the default storage engine, which can be set by the Ignite CLI tool. By the way, if you're not familiar with Ignite CLI, please don't worry, because my colleague will be talking about it in a moment. So let's start with creating a couple of regions. And here I am creating two regions. One is called LSM example, which I will be using to configure the RocksDB engine. And the other one is called B-tree example, which I will be using to configure the page memory region. All other parameters here are not very important. They are only present for demonstrative purposes. And the only notable parameter is the persistent parameter of the page memory data region, which basically allows you to choose between the in-memory implementation or the native persistence implementation of the page memory engine. Here's an example of how we can set the default storage engine using the Ignite CLI. Here I am setting it to the RocksDB variant. Finally, let's create a couple of tables. Here I'm creating a table called cities, which will use the page memory storage engine, and it will be configured with the B-tree example data region. And the other table is the accounts table, which will use the RocksDB storage engine, and will be configured with the LSM example data region. I could have also omitted the engine keyword when creating the accounts table, because this is now the default storage engine, and we don't need to specify it explicitly. Here are some links to the new features and to the relevant documentation. Please feel free to read it and try the feature for yourself.